That's continuation of our discussion of weakly interacting Bose gas. By the way, on Monday you will have tutorial number 2 devoted to calculation of the dielectric function, the polarization operator, which I introduced. Jean-Paul will proceed with you on the blackboard, computing static polarization operator, which is a Reinhardt function, and also discussing closely related phenomena, which are Friedel oscillations and maybe anti-QI interaction, which actually we will need when we discuss magnetism in the last 4 lectures. Okay, lecture number 7. So the general title is Superfluidity. And before, let me discussing the superfluid phenomena, and I begin with actually mentioning experimental evidence of unusual behavior of bosonic system at very low temperatures. Let me summarize what we have learned so far about the non-interacting and weakly interacting bosons. So in the last lecture and the previous one, we discussed first Bose gas without interaction, and we obtained with very simple argumenting that the ideal Bose gas is a subject to phase transition into the Bose-Einstein condensed state, which corresponds to condensation in a momentum space onto the lower levels lying state, if we are saying the trap, to the lowest level of the trap, if we are talking in the box. This is a condensation to uniform state, which corresponds to the delta functional momentum distribution, where delta is centered at momentum equal to 0, which in coordinate space corresponds to the constant wave function. We discussed that globally the condensate can be discussed in terms of general universal wave function. We continue this spirit today, and Bose condensation phenomena occurs when the temperature is sufficiently low, such a way that the Brownian wavelength becomes comparable with interatomic distance. For the temperatures below this T node, which actually, as we discussed last week, doesn't depend on interaction in the first approximation. So below this T node, the de Broglie wavelengths start to be diverging as a function of temperature, and at extremely low temperature, so we have the de Broglie wavelengths becomes comparable with the size of your sample, and therefore you have this condensation phenomena. And putting it on the basis of the phase transition theory, we also said that the wave function can be understood as the order parameter of this system. Again, you will see the same approach will be applicable for superconductors when we discuss the phenomenology of superconductors and describe superconductors in terms of the global macroscopic wave function, which describes whole state of the superconductor. Then, taking into account interaction, we obtain that the interaction actually dramatically changes the excitations. If we talk about condensate, as I said, below certain temperature, there is a macroscopic number of particles which condenses into the state characterized by the momentum equal to 0. However, there are still some particles measured temperature which are, so to say, out of the condensate. So out of condensate particles are characterized also by p square over 2m energy, and only out of condensate particles which are characterized by non-zero energy and non-zero momentum contribute to thermodynamics, to pressure, so to say, to the equation of our state. When we take into account interaction, assuming that the gas is weakly interacting, we introduce a gas parameter n d cube is much smaller than 1, where d is understood as a sort of the scattering length, then we said that interactions dramatically change the excitation spectrum. So the excitations in the weakly interacting Bose gas are sound waves, so which are associated with density fluctuations, and the spectrum or Bogoliubov spectrum epsilon p casts the form c square e square plus p square over 2m square. This is what we have derived, where c is a square root of u for contact interaction p equal to 0 over m times density of the condensate, and if for contact interaction we plug in the expression which we have derived, so this is 4 pi over 3 d cube and u naught over m. So what we see that this gas parameter is there. So the sound velocity is proportional to the square root of interaction, square root of and square root of the density. So with this expression, we immediately see that if Cp is larger than p squared over 2m, which means that the momentum is smaller than 2mc, then the spectrum EP is approximately Cp. This is the sound like excitations for characteristic for the energy of the spectrum for the small moment. However, if Cp is smaller than p squared over 2m, which means the momentum is larger than 2mc, then we have a quadratic, almost non-interacting dispersion p squared over 2m. And then we discussed the decay of these excitations, which are sound waves. And without derivation, just for your information, I told you that these sound-like excitations are well defined in the long wave limit, namely for small moment. Okay, and as we will see, it's very important that the excitations in weakly interacting Bose gas are sound waves. So now let me list few experimental observations which demonstrated that the Bose gas or Bose liquid actually behaves in a quite unusual way at low temperatures. First of all, the first object was helium-4. By the way, historically, the BC was theoretically discovered or suggested in the works of Indian physicist Bose and Albert Einstein in 1924. However, this phenomenon has not been observed for almost 70 years, well, 60-something years. And helium-4, which I'm going to discuss now, was one of the candidates for observation of the Bose condensation. However, it appears that the helium-4 cannot be approximated as weakly interacting Bose gas. It appears that this is a strongly interacting system, and therefore the fraction of condensate in it is less than 10%. And only in late 80s of 20th century, the optical experiment with ultra-cold gases, which we are going to discuss on Friday gave access to the true phenomena of Bose-Einstein condensation, namely discussing the system where 99.9% particles are in the condensate. So you see that there are some obstacles in direct observation of this phenomenon. However, what was observed actually in 1937 is that the helium form, as I said, behaves in a very strange way. First of all, the specific heat or heat capacity, C over temperature, has so-called lambda point. At some T node, which is 2.884, as far as I remember, no, it's 2.18, sorry, 2.884 is from something else, 2.18 Kelvin, demonstrates the shape which resembles Greek letter lambda, namely for low temperatures the specific heat subject to phonons behave as T cube, while around T node it's log T minus T node. So, which was immediate indication that this sort of phase transition in the system. Besides, below T node, there is no boiling of the liquid. So to say, the system is characterized by infinite thermoconductivity. But as I said, this helium form, as it was seen later, is strongly interacting with the system. However, the first indication that some phase transition occurred at 2.18 Kelvin. Then, in the second series of experiment, which was one done by Georgian experimentalist Andronikashvili, he took a stack of disks like this on the axis, and he put it inside liquid helium at temperatures below 2.18, and he started to rotate the system to measure inertia momentum. And he saw a strong deviation of inertial momentum because the liquid has a viscosity. You rotate disks, some liquid is actually dragged by the disks, and this is a way to measure inertia momentum. And what he saw, that the inertia momentum are much smaller compared to what would be seen if we consider just ordinary liquid. Sorry?
What is inertial momentum?
You know, you have the cylinder, for example, which rolls with the body, and it has the solid, how to say it, the rigid body has inertial momentum, which can be defined momentum, which is R times P. This is what it is. This is the inertia momentum. So you have a radius vector and you have a momentum, and the vector product of it is inertia momentum. Okay?
Okay.
The experiment number 3, actually, which gave the title of Superfluidity, was done by Russian experimentalist working in Cavendish Lab in London at that time, Petr Kapitsa, who studied the flow of liquid helium at very low temperatures through the capillaries. Capillaries are pipes with very small diameter, and what he discovered by pushing the liquid helium through the capillaries is if the flow goes with a velocity smaller than some critical value, then the flow goes through the capillaries without friction. So we will see very simple criteria how to derive the critical velocity. However, the possibility for the liquid to flow through the capillary, if you take water and put it through the pipes, you will immediately see that the water has high viscosity, and the water doesn't proliferate through the pipes in your waterproof system without friction. Actually, it creates some friction. However, the helium behaved in a different way in the low temperatures. And the fact that there is no friction and the system goes freely through the capillaries led to the name of the superfluidity.
Excuse me, sir. So in the second case, when it was rotated, you said the moment of inertia was lesser?
Yeah.
Lesser compared to air or in vacuum?
Lesser compared to something. Let me say, at this moment I would probably give you the first explanation which people said, kind of phenomenological explanation in order to explain the phenomena number 2 and number 3, and it was suggested that this is a two-flow liquid. So the helium form consists of two-component liquid. So one component, this is T naught. This one component is just a normal component. This is a density of the liquid, which is the only component at temperatures above T naught. However, below T naught, there are two components. One is normal and another one is superfluid. And existence of the second component, which actually proliferate without friction, resulted in explanation that inertia momentum are small. We will compute inertia momentum at the end of the lecture. So what was said that only normal component, which behaves as normal ordinary liquid, contributes to inertia momentum. And the superfluid component, which goes without friction and is not involved or dragged by the disks, doesn't contribute to the inertia momentum at all. So this is what I meant, that inertia momentums are smaller. So not all density of the liquid contributes to the quantity. And of course, if the temperature is larger than T naught, then the superfluid component disappears and the liquid becomes totally normal. So it basically behaves like water, the liquid which we used to. And coming back to the discussion of Bose-Einstein condensation, it looks like that the phase transition which we are discussing is related to appearance of the superfluid component. So this is a transition to the superfluid state, and what we are going to discuss today are different manifestations of superfluidity and simple explanations of this phenomenon. Okay?
In part 3, which kind of, you said that the fluid flows without friction. Is it between the particles, the layers of the fluid? Or
No. These are completely different experiments. This is a container, cylindrical container, where it's rotated. And here, it's a system of capillaries. So to say, the container is here, and the pressure is applied such a way that the liquid is pushed to flow through the capillaries with a certain velocity. You have a sort of piston, you push this piston and liquid goes up. So it's two completely different sets of experiments.
So I'm like, as when it is pushed, is where I just want to know where there isn't friction. Is it friction between the layers of the fluid or the pipe?
We discuss it. So the friction means that the liquid flows through this pipe and there is a possibility to emit phonon inside the wall of the pipe. So this is how friction appears. You lose the energy because you emit phonons in the pipe. So to say your pipe, you heat it, and since you transfer some energy into the pipe, the energy of your flow becomes less and less. Therefore, it suffers from friction, it reduces velocity, and so on and so forth. However, this system behaves differently. Namely, you push your flow with a piston, and controlling the behavior of piston, you actually controls the velocity of the flow. The stronger you push, the stronger you create the pressure, the faster liquid flows. So it was seen that if you do it very gentle, if you do it very slow, then the velocity, the energy of the liquid is the same. So it does not decay, in a sense, it does not, it is not a subject of friction. Actually, it creates a big problem for helium in these dual containers. One needs to seal it very carefully, because if you have any crack, any something, any little hole, then the liquid will try to escape because of this superfluidity. Besides, in addition to that experiment, there was a similar experiment which is called Thermo Mechanics. So if we make two containers, A and B, and create a pressure and temperature in one container as P plus delta P, and T plus delta T. So to say, we heat it a little bit, we pump it a little bit, and there is a capillary which is connecting containers A and B. And in A and B, you have a pressure and temperature like that. Of course, containers are big enough to assume that the systems in container A and B are in thermodynamic and mechanical equilibrium. But what typically happens is, we know that if you have one container which is hotter and another container which is colder, then the hot substance goes to the cold container in order to heat it. This is how the equilibrium is established. However, in this system, it goes other way around. There is a flow from cold container to the hot container, which goes in order to cool down the container. I'm not saying that this is a violation of thermodynamic law. This is a low flow. It's two liquids. One is normal and one is superfluid. And superfluid liquid actually goes from cold to hot. Of course, total entropy does not decrease. There is no miracle and there is no violation of the basic laws of the nature. However, the appreciate flow from cold to hot was discovered. Do you think it's unusual? Or?
I think for the part B, where it is in superfluid state, it sees less friction, so it's easier for it to go to A.
Yeah.
So it just, I think, it struggles between the pressure versus the friction cost. So
one needs to have something. I mean, if the density of your liquid is just a normal density and you don't have superfluidity, you don't absorb it. So the unusualness of the behavior of system is totally related to existence of this superfluid component, which itself is related to existence of Bose-Einstein condensation. You have a density of condensate there. And besides the last effect, which I would like to mention, this is called so-called containing effect. So there is a pipe which was put inside the liquid helium, which was cold. So this substance was cold. This is helium-4, and it was hot outside. And there was so-called containing effect, again related to the proliferation of the superfluid component through the capillary. So liquid, cold liquid, goes up and contains through the capillary in the hot area. So this is thermomechanics. in order to explain all these phenomena in a phenomenological spirit, without yet some microscopic theory, there were two assumptions. So instead of one component liquid, we are dealing with a two-component liquid. One component is superfluid and one is normal. And the second assumption is that the spectrum of excitations necessary to explain the experiments has a form characterized by, this is epsilon p and this is p, sound like excitations and small momentum, and another minimum which we discussed at the end of this lecture. So to say the low-lying excitations are phonons, so associated with change of the density. I think you understand that to have phonons one doesn't need a crystalline lattice. We have phonons in this room, I speak, and sound wave propagates. And yet another minimum is called rotons. We discuss it a bit later. So these two assumptions were sufficient in order to describe the experiment. Okay, I would like to keep this spectrum. You see that Bogoliubov spectrum, at least at very low momenta, is similar to what was suggested phenomenologically in the first half of 20th century in order to explain this unusual behavior of the liquid. So now we come to another small paragraph which I would call Lambda Criterion. It's very simple. So let's zoom in the pipe. We introduce two coordinate system. One coordinate system, so there is liquid which flows with the velocity w. So we introduce one coordinate system and coordinate frame 1, which is associated with flow. So the flow flows with constant velocity. We can take any inertial system which we like. So we introduce the first system, which system of attached to the flow. And the second system, or laboratory system, will be attached to the walls. Okay, as I said, in order to get a friction, we need to create excitation to the walls. And this excitation should be characterized by energy E, P. So P is a momentum, P, which is HQ, is a momentum of the quantum liquid, the momentum of the excitation, and epsilon P is energy of the excitation. We don't yet know what kind of spectrum of excitation it is. We will check with the different spectrums and find the criteria when these excitations are possible and under which condition. Okay? So we write the energy of this excitation in the system associated with the pipe. So this is number 2. So this is energy of the excitations E prime P in the system associated with the flow, plus P times W, plus we have a kinetic energy of the flow, so we write total energy over 2. So this is energy of the flow and excitation in the coordinate system 2 recalculated from the coordinate system 1. Again, in the coordinate system 1 the flow is in the rest, so it doesn't move. However, in the system of pipe, flow moves, and therefore this is how it looks like. So, but in the system of pipe, the momentum in the system 2 is equal to minus momentum of the excitation in the system 1. This is momentum and energy of the excitation. So, yeah. P. Let me say it this way. So therefore, I will rewrite this criterion is EP is equal to E prime P minus P since it's prime minus P dot W plus M W squared. And in order to be able to create the excitation, this part should be negative. So the criterion to create excitation in a pipe, we should have epsilon P prime minus P W, epsilon prime should be negative. Or the velocity should be larger than epsilon prime P over P, and this one I will call the critical velocity. What I'm saying is that you create excitation with this energy, and if you are able to do it, you reduce the total energy, so your total energy of the flow is now smaller than kinetic energy, and this is why you lose the energy you have a friction. So the velocity of the flow should then be larger than certain critical velocity. We will see it the very same way that for superconductors there is a critical current. You apply the voltage to the system, and if the current exceeds certain critical value, the superconducting state is destroyed. So let's now, and this simple criterion is called the Lambda criterion. I didn't compute any integrals, nothing. So let's examine for what kind of excitations this critical velocity acquires non-zero value. So whether it's possible for any system or there is certain condition. Are you with me? Okay, let's start with ideal Bose gas. Ideal Bose gas. Epsilon prime P is equal to P squared over 2m. So therefore the critical velocity is epsilon prime P divided by P is P over 2m. However, we want to create excitation with arbitrary small momentum. So therefore, if we consider this equation in the limit momentum goes to 0, we get that critical velocity is 0. We take a limit of 0 momentum, and we say that for ideal Bose gas or ideal Bose liquid, no interaction, whatever velocity of the flow you create, and this is controlled by piston, the excitations will be created immediately because the critical velocity is 0. So therefore, the ideal Bose-gas system without interactions is not at all superfluid. So one should not mix phenomena condensation and superfluidity. They are very close and very much related, but they are not the same. Let's consider second example. Weakly interacting Bose-gas. Bose-gas plus weak interaction. We have this. So the critical velocity is epsilon prime p divided by p, and we take a limit p goes to 0. We divide Cp by p, and we get C. So in contrast to ideal Bose-gas, in slightly non-ideal Bose-gas, where the low-lying excitations are phonons, so sound waves propagating with a linear dispersion, we see that in accordance with Down Criterion, the velocity of the flow should exceed certain critical value, which is sound velocity. If we push flow faster than the sound velocity, and sound velocity is determined by the density of condensate and interaction, then the superfluidity is destroyed, and you start to create, you start to probe the normal component. Well, you destroy the superfluidity. If, however, the velocity is smaller than the critical one, and all these calculations done at 0 temperature, then what you see is, indeed, if you push the liquid to flow with velocity smaller than the critical one, then it proliferate through the pipe without friction. Okay? So the conclusion is that in order to have superfluidity, one needs to have interacting system which guarantees you the sound-like excitations in it. So if we are back to the phenomenological spectrum, Landau spectrum, we need to be a little bit more sophisticated. We need to put a tangential, because there is another minimum, and the critical velocity will be defined by the tangential to the system. We come back to this a bit later, and we discuss more about that on Friday. Okay, so let's now come back to the description of the condensate and introduce you to another phenomena, namely existence of vortices. So vortexes, which is again closely related to the superfluidity.
Excuse me, sir.
Please.
In this case, when our W, the velocity is less than C, in the second case, from this it seems that in the frame of reference 2, the pipe frame of reference, the kinetic energy of the fluid is not just the kinetic energy but some energy factor.
You just don't create excitation, nothing goes to the wall.
Okay, okay. That would, okay.
So this is written on the assumption that something goes.
Okay.
But if nothing goes, this is 0 and this is 0. And you just have the same energy in system 1 and in system 2.
Thank you, sir.
Okay, let's come back to discussion of the global wave function. So today lecture is a bit unusual. In a sense, we will not proceed with a lot of calculations, but we have a lot of interesting physics behind to discuss. Okay, what I was saying is that let's introduce the de Broglie wavelengths lambda, which is h bar over square root of to mt. And we are saying that as long as the de Broglie wavelength is smaller than the interatomic distance, so this is inverse cubic root of the density, then we can speak about bosons short length waves or particles. As I said, in this limit we have wave packages. We can say that these are particles. However, if so, this is temperature, as you may see, above T node. However, if the temperature is below T node, then we see formation of the giant matter waves. So if lambda is larger, and in fact much larger than n to the minus 3, again, all what I'm saying is related to three-dimensional case. Two-dimensional case is a bit tricky. One needs to speak about Kosterlitz-Townley transition. This is universality class of XY model, what we probably discussed with Professor Nersesyan. Again, I'm not going to dwell into very interesting but much more complicated physics now. I would like to start with the simple things. So this condition assumes that the temperature is smaller than T node, and then only then we can characterize our system by the giant wave function. So for this sake, we derived the Gross-Pitayevsky equation. So I d psi over dt, which is equation characterizing the interacting Bose system, is equal to minus delta over 2m plus Vr minus mu plus g psi square times psi. This is Gross-Pitayevsky equation. It accounts for interaction, so this is sort of nonlinear equation, and it accounts for the potential. So we assume now that we have a box, very, very large box with infinite walls. And of course, we are looking for stationary solution. Namely, we say that our wave function doesn't depend on t, so therefore the time derivative is 0. And we are looking for homogeneous solution, which says that the wave function does not depend on coordinate. Therefore, our equation, nonlinear Schrödinger equation, becomes much simpler. For this sort of potential, inside of potential, it's 0. So we just have equation that g times psi squared is equal to mu. Therefore, psi as a wave function is just a constant. Let us say psi node. And in principle, since the wave function is a complex function, the square modulus wave function describes the probability density. What else we can write that this is a case. So we are saying that the wave function is a constant, but of course this equation should be accompanied by the boundary condition is equal to 0. Therefore, very close to the wall, the wave function should go down and actually should go down this way in order to provide the nullification of the wave function. You remember when you did your quantum mechanics, you consider particles in the box, you find that the functions are sine and cosine. Here it's a little bit different because we don't have linear quantum mechanics anymore. We have Gross-Pitayevsky equation. By the way, this length, psi, where the wave function saturates to the constant value, is called Healing length. And maybe we spend some tutorial, I show you how to solve the nonlinear Schrödinger equation to get a tangent function, which then will lead to, this is nonlinear equation. Again, unfortunately I don't have time for this now. What is important for me, that away from the walls, so for the distances larger, if x is larger than psi, so this is 0, the wave function is constant. The wave function changes dramatically on a scale of psi in the vicinity of the wall. So I'm not about to discuss that. I'm about to discuss the behavior of the wave function in this domain. Okay? Now I would like to define a mass current, J. This is h bar over 2m. By the way, if I want to restore h bar in this equation, I put h bar here, and this is h square nabla square, which is delta. So this is kinetic energy, and this is what we have here. This is I, so this is psi gradient psi bar minus psi bar gradient psi. So this is the current quantum mechanical operator of the current written in terms of the wave function. You are familiar with this from the classes of the quantum mechanics. But since the square modulus of the wave function gives us the density of condensate, so without losing generality, I can write it down. So this is n node over r. Then the square modulus, you remember that we got mu is equal to gn. This was our Pines-Coogan-Lawrence theorem. Therefore, n node r, I to the I chi over r. So if we allow small fluctuations and deviations of the density and small variations of the phase, then both modulus and phase should be assumed dependent on the coordinate. However, I said that I'm dealing with uniform solution. And with the first approximation, I will say that n node of R is approximately equal to constant n node. So I will ignore the coordinate dependence of the condensate. So if we do that, then J is equal to h bar over 2m I. I plug in this wave function here. I don't differentiate the prefactor of the exponent, so I will write n node here, and I have I chi gradient minus I chi minus n node e to the power minus I chi gradient I chi. So I continue it here. So I write it as h n node over 2m I. So the gradient of exponent will give me I exponent times gradient of chi with a sign minus. so I have minus I, and exponent them cancel each other, gradient of chi, and the second term will give me another minus I, gradient of chi. So the exponents, since this exponent is with plus and this one is with minus, they cancel themselves. So I times minus I gives me 1, so we have h bar n node over m times gradient. And I would like to write it that the current as n node times superfluid velocity. I'm dealing with a superfluid current because it is related to the global wave function of the condensate. Therefore, I can write down that the superfluid velocity is h bar over m gradient of chi. So the superfluidity velocity is associated with the gradient of the phase of the wave function. Again, we said that for very small, very low temperatures, we have the de Broglie wavelength of our package, which is huge, which is macroscopic. Therefore, we are allowed to describe our many-body system of bosons by unique global wave function, which depends on one coordinate only. With very general form of the wave function, which is modulus time phase, we then derived that the superfluid phase is associated with the gradient of the phase of the wave function. Okay, so far so good. Let's see what are the consequences of this. Again, doing nothing or almost nothing, we will derive and almost for free some very important properties. So first of all, let me apply operator nabla vector to Vs. So this will be h bar over m nabla times nabla times Vs. Sorry, nabla times gradient chi, and the vector product is 0, so you know that the circulation of the gradient, so this is 0. Which means if you take some surface, then integral Vs nabla Vs ds. So this is surface and this is, so to say, normal, and ds is ds times normal vector as usual. Thanks to Stokes' theorem, we have this as an integral Vs over dl. So dl is element of the boundary. So this is a Stokes theorem. Okay, so if you have a potential flow, then there is no singularity and this is a 0. However, let's think, is it clear? Without singularity potential flow, this integral should be 0. Suppose we take now a container. We take a cylindrical container with a superfluid helium, like an experiment I said, and start to rotate this container. If we look on the container from the top, if anything happens, it can be only in the center of the container. So we take a small, this is a top view on the container. We take the circle C1 and circle C2, and we are saying that this integral, the integral of a boundary, which is equal to 0, because we assume in this area the flow of the liquid is potential. So we are saying that the integral over C1 Vs dl is equal to, well, minus integral over C2 Vs dl is equal to 0. Minus because one contour is taken clockwise and another one is in counterclockwise. So we're just replacing the flow through the surface by the integral over boundary. We have two boundaries, outer boundary and inner boundary. There is no singularity, so we have this condition. Of course, when we rotate, then the velocity flow is tangential. So we can write this condition that the integral is 0 as Vs times 2pr. So Vs, let me be more pedantic, Vs over r1 times 2pr r1 is equal to Vs over r2 times 2pr2. So this equality can be satisfied if and only if Vs of r is some constant divided by r. And we are about to quantify this constant. So in addition to the potential laminar flow, we found that existence of superfluidity can also lead to some singular solution. So this is why I said I should exclude the centrum of container. So the field of your velocities can also assume the singular solution with a singularity 1 over r. And it follows from the Stokes theorem. And of course, if the velocity is larger than something, you destroy superfluidity. You don't have superfluid component anymore. So what we get vortex. So if the velocity exceeds angular velocity when we rotate container, this is what we estimate at the end of the lecture. If you rotate it faster than something, we create a one vortex, which consists of the core of the vortex, where there is only a normal component, because we destroy superfluidity in the middle. And then the velocity field actually depends on r, this way. Is it clear? Again, everything what we get is just from the superfluid behavior, that the wave function is just modulus times the phase, and the superfluid velocity is associated with the gradient of the phase. Let's write the gradient. So we say that Vs is h over m gradient of chi, and psi r is square root over n node I to chi. Let's write the gradient in polar coordinate system. Since we have a cylinder, it's quite natural to assume that we are working in cylindric coordinate system, and therefore the operator nabla, which we need here, should be written in the polar coordinate system. The polar or cylindrical coordinate system is that if I take the plane, so this is z direction, then in the plane we have x and y. X is r cosine phi, y is r sine phi. This is connection between Cartesian and polar coordinate system. So tangent phi is equal to y divided by x, and r squared is equal to x squared plus y squared. Of course, we have a z component as well, but z component precisely in the way like it is in Cartesian coordinate system. So the nabla operator is equal to, we should define ort in direction of r. So this is d over dr modulus plus ort in the direction of phi. This is 1 over r d over d phi. And this is ort in the direction of z, d over d. Okay? So, as I said, we have velocity which is tangential. So only phi component exists in the plane. So therefore, we should assume, without any losing any generality, that your phase chi is some another constant, let me call it beta times phi, where phi is a polar angle. So, if it is like that, so then you have your superfluidity velocity, which is 8h over m. The gradient phi is then 1 over r times beta. Because d over d phi, so now I'm about to connect alpha and beta. Okay? So I already reproduce the form of superfluid velocity. However, the wave function should be identical under rotation over 2 pi. If we then replace phi by phi plus 2 pi, nothing happens, right? Therefore, we should say that beta is equal to s, which is integer number. I can add any times 2 pi multiplied by integer number, and nothing happens with the wave function. Therefore, I'm saying that alpha is equal to h over m times integer number. Okay? And the last step, I'm computing circulation over superfluid velocity field times dl over arbitrary circular contour. This is 2 pi r times vs, which is h squared over m times s times 1 over r. R cancels out, and this quantity is called gamma, So the integral over boundary. And what you see is that the circulation, which is integral of the superfluid velocity field over boundary of your contour, is quantized. So what I obtained is quantization of circulation, because gamma is proportional to some integer number times h bar. I got quantization of circulation. So you see that first of all, superfluidity is a quantum phenomenon. This is a quantum liquid. And as a result of quantumness of the behavior, I got a quantization of circulation. Okay? So this is how I introduce vortices. Vortex. But of course, if we start to rotate faster and faster, we create another vortex, and so on and so forth. And let's now understand how these vortices interact between themselves, and whether it's energetically favorable to create a vortex with a large S, or it's better to create a few small vortices with small s. Just doing that. In order to do that, let's compute the momentum and energy of the vortex. So sorry, it was a bit confusion when I spoke about inertia momentum. Inertia momentum are characteristic of rigid or fluid body. So this is continuous object. Now I'm going to say about momentum, which is defined R dot P. It's not inertia momentum, this is a momentum. This is. So as I said, what I'm going to discuss now, this is analogous of this R dot P for continuous system. So again, we assume that we have a cylinder. So this is 0, this is L. We know from here that we rotate this cylinder, and the field of velocities is tangential. It doesn't depend on z at all. And therefore, if r is in the plane, so r times v creates a momentum in direction of z, because this is a vector product. This is r, this is p, which is vs over m, and the vector product over r dot p is directed along z-axis. So therefore, I can write down that m, which is by definition mz, I integrate over z. This is integral, and this is integral from 0 to r node. R node is the diameter of the cylinder. I have a density. So first of all, I have 2 pi r dr. And then I have r times rho s times vs. Yeah. Rho s times vs. Rho s, which depends on r, and vs depends on r. So this is modulus of the momentum. I don't have mass. In order to get a mass, I have to integrate the density over some volume. So vs is, this is 2 pi L integral from 0 to r node, r dr. I have r rho s, which is a density and which is a constant. It doesn't depend on r. And I have h squared over m times s times 1 over r. Okay. So r cancels out. So the momentum is then 2 pi L rho s times h square over ms. And the remaining integral r over r dr gives me r naught square half. So what I have here, pi r naught square L times rho s times h square over ms. So this is a volume of the cylinder, right? Volume times, yeah. Question?
But if it lies in the z direction, why do you have to carve out an interval and the boundaries are in another kind of axis? Like
We don't have an integral over r. I mean, as I said, in z it's uniform. So I'm only saying, well, it's proportional to the length, so it doesn't depend on z. Therefore, because this is a density, in order to get mass, I should integrate the density of the volume. The integration over z is straightforward because nothing depends on z. This is why I wrote L from very beginning. So everything can be obtained by cutting the cylinder by planes perpendicular to the z. So in each cross section we have a flow of the velocities which are in the plane. So the integral over d volume is integral in the cylindrical coordinate system dz r dr d phi. This is element of volume. So nothing depends on phi. So this is why I wrote 2 pi. Nothing depends, so this is dz. Nothing depends on z, therefore I integrate it over z and get L. So this is L and 2 pi are already there. The remaining thing, which everything depends on the radial component, radial vector. So this is why I wrote dependence on R explicitly.
Excuse me, sir.
Yep.
So in this problem that we have introduced, we have kind of rotated the superfluid such that it's rotating circular in a circular fashion, and even while calculating Vs we used such that because of the nature of our problem we are using a circular contour. But is this a problem that is general for any kind of rotation, so that we can introduce some other kind of contours?
Look, I said the cylindrical because it respects a symmetry. You may ask me the question if we take the box and start to rotate. The box does not respect cylindrical symmetry. You have corners. So you reduce your symmetry to the square. In corners there will be some turbulence, and in order to avoid any discussion of the corner effects, I assume that the symmetry of container is the very same as the symmetry of the problem, namely symmetry of the vortices. This is why I took a glass or cylindrical container. Of course, we can pose any problem we like. However, the solution of the problem with the reduced symmetry will be more complicated because I need to take into account what's going on around sharp corners. And I want to avoid that.
But sir, even after taking a cylindrical thing and rotating it in a circular fashion, the contour while calculating Vs can be anything, right? We are just making our life easier by just taking the phi component and other component.
Yeah, but for any other contour you need to do more sophisticated calculations. For simplicity, I took, since nothing depends on phi in your cylindrical coordinate system, I took a contour where also nothing depends on phi. If you have a more sophisticated contour like that, of course you will get the same, but you need to write explicitly dl for this contour, and you need to write explicitly v at r in each point of this contour, but you will get the same.
Yeah, the gamma would be s, like
Yeah. Because you can, well, for those who are familiar with basics of topology, you can deform your contour in such a way that it has the same property. And as long as you can continuously deform the contour, for example, on a sphere, this is what you probably discussed with Professor Nersisyan, you can take any contour like this. But you can continuously deform this contour to the point, as long as you, And this is actually the essence when you do your Gauss theorem you construct the electric field of the isolated charge. The electric field has a radial structure, and therefore you integrate of a sphere using Gaussian theorem, and you get that your induction of electric field is 1 over r cube. Yeah, whatever. However, if you want to construct tangential fields to the sphere, so if you want to construct tangential fields to the sphere, which is smooth in each and every point, you will not be able to do it, because it's impossible to make a tangential field to the sphere. It can be smooth in each and every point except the poles, one of the poles. So you have a string, and this string is nothing but Dirac monopole, which directly related to the fact that one cannot construct smooth in each and every point tangential field to the sphere. There is always a string or monopole over time. So all this related to topology, and there is a lot of topology in the definition of vortices, as you said, as long as the contour can be deformed to the circle, but you can proceed with calculations with any circle you like. There. For example, you can replace this contour by this contour, assume that there is no flow through this area, therefore integral over this circular contour will be immediately equal to the integral of your very sophisticated deformed contour, and this is how you get your result using this Gauss or Stokes theorem. Is it clear? But this exercise which I did has very important conclusion that your momentum is quantized. And it quantized with S. Let's compute the energy. So M is proportional to S. Let's compute the energy. In the same spirit, energy is integral over d volume. Let me write it this way. And this is rho s vs square over 2. So this is just a kinetic energy. So this integral is therefore 2 pi L integral to the R node. And let me write question mark in the low limit. You will see why I'm doing that. This is R dr. This is rho s. And then I have h square over m s square 1 over r square. So this is a velocity field, right? This is 2 pi. Sorry, there is also 1/2. 1/2. I cancel this 2. This is pi L rho s integral to the R node from the question mark. This is h square over m square s square times r 1 over r square dr. So I see that the integral, which I'm about to compute on the next line, is divergent, because the integral is dr over r, it's logarithmically divergent, therefore I should take the cutoff, and at the cutoff I will use the radius of the core of the vortex. We are saying that there is no superfluid component in the centrum of container. So this is then pi L rho s times h square over m square s square times logarithm r node over I. So what I obtained is that the energy of the flow in the container logarithmically depends on the size of a container. On one hand, and it depends on the square of the integer number, while the momentum depends on the first power. So energy then is proportional to S squared. What is more important? So therefore, I make very important conclusion from this observation. Suppose we have two vortices characterized by S1 and S2. Can they merge and form one bigger vortex or not? Do they attract or they repel? If there are two vortices with a quantized number S1 and S2, then the total momentum of this vortex will be proportional S1 plus S2, because the momentum is conserved. However, the energy of this big vortex, S1 plus S2, will be proportional to S1 square, S1 plus S2 square, which is larger than S1 square plus S2 square. Therefore, the conclusion is that it is energetically unfavorable. This is E1 plus E2. So since the energy of the big vortex is larger than the energy of two separate vortices, it is energetically unfavorable to merge two vortices in one. Therefore, the vortices repel themselves. So the interaction between vortices is repulsion. It's not attractive. Okay? And therefore, it's energetically unfavorable to create vortices with large momentum, with large numbers. So it's much more favorable to create many vortices with a minimum S. So you start to rotate your container, and then you start to create vortices. So each of them are characterized by certain circulation. So if this and all these circulations are the same. And you see that in the vicinity, this circulation compensates. Therefore, if we integrate over all vortices, everything inside cancels out, and the only thing which remains is on the boundary, and the vortices don't merge, they repel themselves. Let's make a last step in the last 2 minutes, and let's assume something like Lambda Criterion. So how fast you should rotate your container in order to create the first vortex. Of course, if you have a superfluid and if you do it extremely slow, nothing happens. So you need to rotate it faster in order to make the first vortex line. So the same way I can write down that E is equal to E prime plus M times omega. So this is angular velocity, omega, and this is this momentum M. The very same way I'm coming from one non-inertial system to another one, and should write down that E prime minus M times omega should be negative. So the critical velocity, omega c, is equal to E prime divided by the momentum, which we computed. So E prime is this energy. So this is h squared over m squared, and I will take s equal to 1, because we said that it's energetically unfavorable to create pi L rho s times logarithm r node over r. And this is what I have for the energy. And for the momentum, we have pi L r node squared times h squared over m rho s. So pi L cancels out, rho S cancels out, and h square over m in the first power cancels out. So we obtain that the critical velocity is h square over m, 1 over r naught square, logarithm r naught over m. So this is the angular velocity one should use in order to create one vortex in the system. And you see that it depends logarithmically on the r. Okay, that's all what I wanted to discuss today. I think it was a very interactive lecture. I'm glad that you asked many questions. We come back to the same questions on a bit different levels on Friday when I show you how the superfluidity is measured in cold gases and so on and so forth. However, recapitulating briefly what we discussed today, we actually found a very simple way to explain superfluidity based on the sound wave of excitation. We have found the Down Criterion, which says that its flow is slower than the critical velocity, then there is no excitations created in the walls of your pipe. This is how superfluidity can be explained. And then we discovered that the superfluid part can be described by the global wave function, which accounts for the uniform condensate. We have seen that the superfluid velocity is quantized the same way as a circulation is quantized. So the field of velocity is singular, which is vortices, and we see that the interaction of vortices is repulsive. And the very same way we have estimated the critical velocity necessary in order to create one vortex. Okay, any further questions?
Can you please just explain how the energy how two vortices repel each other according to that?
Yeah, we said that in order to create the
big
vortex with a momentum S, angular momentum S, m, which is pi rho S L R naught square times h square over ms. So suppose you create the vortex with a quantum number s corresponding quantized angular momentum m. And you create another vortex with momentum s2. So the question is now, these two vortices, when they approach each other, what they are doing? There are two options. They can attract each other and therefore collapse in new bigger vortex. But since momentum is conserved, the new bigger vortex, which is a result of collapsing of two vortices characterized by momentum S1 is S2, should be characterized by momentum S1 plus S2. Momentum is conserved. But let's see what is the energy of this big vortex. The energy of this big vortex is proportional to this integer number square. Therefore, it should be proportional to the S1 plus S2 square, which is S1 square plus S2 square plus 2 times S1 S2, and 1 S2 are positive integer numbers. Therefore, we see that the energy of such a big vortex created out of two vortexes is bigger than the energy of two separate vortexes. Therefore, it's energetically unfavorable. So would it be opposite if energy of two vortices will be smaller? Well, if the energy of one big vortex will be smaller than energy of two separate, it's kind of bound state. Your vortices then would form the bound state, or one big vortex. It doesn't happen, because the energy of two separate vortexes is larger than the energy of big vortex created of two separate is bigger than the energy of two individual separate vortexes. So the process is energetically unfavorable. Therefore, the vortices must repel each other. They cannot attract. They cannot form bound state. They cannot approach each other because they repel. They don't want to come closer. And therefore, what I'm saying, that instead of creating a huge vortex with large momentum, by this energy conservation law, it's much more favorable to create many small vortices with a small momentum, S1. Because if we compare the configuration of, say, 5 vortices, each of them characterized by S equal to 1, and all possible other configurations like 4 vortices, 1 is with a quantum number 2, and 3 another with a quantum number 1, or 1 big with a quantum number 5, all these configurations are less favorable. So what we do when we start rotating the container, we create more and more simple vortices with S equal to 1. This is what we do. And we will see that this phenomenon is closely related with the superconducting phenomena, when the magnetic field doesn't penetrate through superconductor. However, magnetic field can create vortices in superconductors, in type 2 superconductor. And this vortex lattice, which is created, so superconductivity is partially destroyed in the core of the vortex, is precisely the same phenomena as superfluidity is destroyed in the core of the vortex. And we create sort of vortex lattice in the system when we rotate faster and faster.
Excuse me. Just a curious question. Like, when you say we are merging two vertex to create one, each vertex characterized by a quantum number S1 and S2, how can we say that the quantum number of the big vertex is summation of S1 and S2 about the...
Because momentum is conserved. You have conservation laws. You conserve angular momentum and you conserve energy. So from the conservation of angular momentum, if you have a momentum 1 and momentum of 2, the momentum of the big vortex should be equal to sum of the momentum. And each of them is proportional to S. Therefore, the momentum of big vortex is its assumption. So what I'm saying, suppose that two vortexes with a momentum S1 and S2 can create a bigger vortex. If it is so, the momentum of this bigger vortex should be equal to S1 plus S2, because the momentum is conserved. Or they cannot create. If they cannot create, and this is what happens, we just have two separate momentums, which is the same as the energy tells us that they cannot.
I'm getting confused about something. Here you are explaining you explain in terms of two vortices that they repel each other. It's like you are not like creating, and you explained that you use a magnetic field creates the vortex, so you have exposure to the. Okay.
Let's postpone superconductivity till beginning of March, because for superconductivity, first of all, you will need to learn that the superconductivity is formed by Cooper pairs. Cooper pairs are pairs of two electrons, and by the way, with a very long coherence length. So we will see that Cooper pairs are not isolated object, but it's kind of soup of Cooper pairs. But being created out of two electrons, Cooper pair is charged. It has a charge of twice the charge of electron. Therefore, being a charged quasi-particle Cooper pair actually fills the magnetic field. And this magnetic field actually will do the very same, that is, take it for granted. The magnetic field for superconductor will do the very same job as rotation is doing for the condensate, for the superfluid. Because I don't discuss any charge, nothing. I'm saying I have a neutral liquid with the two components, normal and superfluid, and I rotate the system, and what happens that as long as the rotation angular velocity of rotating of container is small enough, nothing happens with superfluid component, nothing at all. However, I start to rotate faster and faster, and first thing is happening, I create a vortex. So assuming that container was filled in just superfluid component, nothing else, zero temperature, I'm in this regime. So all liquid is superfluid. I start to rotate it, I rotate faster and faster, and what I create first, I create a vortex line in the centrum. So I destroy superfluidity in the center of the container. It exists everywhere else. So I create a core with a radius A, where the liquid is normal. and it's still superfluid everywhere else. And this structure with the field of velocity decaying as 1 over r is the vortex. This is what I did. I rotated faster, and the question is, what then happens if I start to rotate faster? Would this vortex grow and get a number 2, 3, 4, 5, or it's more energetically favored to create a second vortex, third vortex, fourth vortex, fifth vortex? And I'm arguing that from the energy conservation arguments, it's energetically favored to create many vortexes instead of creating one large. Because for momentum it's the same, for energy it is not. Energy tells me that system of small, many vortices is much more energetically favorable than large, big whirlpool or whatever. It's just a matter of quantization. Think about it. And since these vortices cannot merge, they repel themselves. They cannot attract. Because would they attract, they will come closer, closer, closer and collapse in a big vortex. And it doesn't happen. Quantization forbids me doing that. Okay. You? Mm-hmm.
Because I just want to ask, is it, from your derivation, is it correct to say that the momentum and the energy that you derive does not depend on the superfluid velocity?
No, it depends. You see, this is dependence of a momentum, of a superfluid velocity, angular momentum, and this is dependence of energy. By I plugged in the dependence explicit expression for velocity, which I derived. So the superfluid velocity I integrate over all volume of container. Superfluid velocity changes at each and every point depending only on radial component. But if I want to compute macroscopic extensive quantity, which is energy of the total angular momentum, I integrate over volume. So dependence of superfluid velocity, so Vs, is h squared over m times s times 1 over r. So it depends on r, doesn't depend on phi, doesn't depend on z, because it respects the cylindrical symmetry. This is explicit dependence of angular velocity taken in each and every moment, every point of the space. However, I integrate over volume. So and at the end of the day, it depends on s. For example, energy depends on s squared, momentum depends as linear, and that's it. It depends on superfluid density, it depends on mass, it depends on h bar, and so on and so forth.
The S, you said the S was an integer. Is there any physical significance for the S?
Sorry?
The S is an integer, no?
Yes, yes.
I mean, is there...
S is quantized, S is integer number. My superfluid velocity, which behaves as 1 over r, is quantized, so it takes the value allowing S being integer number. It is closely related to quantization of circulation, quantization of the flow through the surface. Flow is also quantized. As a result of quantization of velocity or circulation, we have angular momentum being quantized, and we have energy being quantized. But quantization tells us that the angular momentum is quantized being proportional to the first power of the integer number s, while the energy is proportional to the second power of the energy of the integer number s. I compute macroscopic quantities. So this is integration of a volume of a whole container.
Is there something special about creating the first vortex at the centrum of the cylinder?
No, it's just a matter of symmetry. The symmetry, if you look from the top, where else you can create it, you rotate it this way only in the centrum. Because why? So you look from the top, and your container is rotated this way. If I create vortex here, Why should it be? Because it doesn't respect the symmetry of rotation. Then the only possibility is to create it on the center, because then whatever I do, the symmetry is preserved.
But afterwards, you are creating more vortexes at any other point.
That's a good question. It's a good question. The quantization out of creating the first vortex is a bit complicated problem. That's a good that you asked. But in principle, you can have that the vertex lines kind of form a chaotic stuff. But in principle, what I can say that at the end of the day, you will have a polygon actually embedded in your lattice. So first you have a triangle, then you have a rectangle, and you have a polygon. At the end of the day, your vertex will be like that, and we will come to this point again in superconductors. Vortices form a hexagonal lattice. So if your question being translated to proper language sounds, at the end of the day, when we created many vortices and we assume some lattice. So 2 or 3 or 4 or 5 is not yet a lattice. But at the end of the day, when we create many, what kind of lattice is it? It's a hexagonal lattice. We will see it with superconductors. It also related to the minimal configuration. And actually, when the first suggestion of the vortex lattice on superconductors was done, it was a mistake. It was assumed that it's square lattice, and actually it appeared that configuration of square lattice is characterized a bit much higher energy. It's a matter of third digit after the comma. And the minimal configuration is related to the hexagonal lattice. We discussed it in superconductors. Any more questions? Think about it. I'm giving you some food to think. And also, I deliberately do the spirit, that we do some estimations, we do some very simple calculations. There were no any kind of complicated calculations today. However, we actually came to several very important conclusions just based on estimation, on symmetry arguments, on the behavior of mathematical object like velocity field, possibility to have a certain singularity, Stokes theorem, Gauss theorem, yeah. By the way, electric conduction is 1 over r cube, because r square, sorry. I said r cube. When I gave this example with a point-like charge, you write like E times the surface of a sphere, and this should be equal to charge, and there is a coefficient of 4 pi, so induction should be 1 over r squared. Doesn't matter. Okay, I should turn it off.